So, any questions?
Yeah. We have seen in U1, in U1, we do U1. We have seen that
U1.
Group elements also.
Yes.
So, can we find the notion of distance? But for U1, the Cartesian form goes to 0.
Yeah.
How is this possible?
Okay, the Cartesian metric is 0. That is true. Yeah. That is true. But I mean, that is yeah, that's true. Yeah. But I mean, you can define another metric which is just the length of the circle, right? I mean, that is fine. But I mean, the Cartan killing form is 0. That is a fact. But that is not the metric that appears on the circle.
So if I compute Lorentz group, Cartan killing form, should I be given the ordinary metric in physics?
Well, I mean, so this Cartan killing form will be on the Lie algebra, right? But the Lie algebra is Lorentz group is 6-dimensional, right? So that is the metric on the 6-dimensional space.
So this Cartan killing form metric is different concept from physics.
It's a metric. Let's call it Cartan killing form. Yeah? Cartan killing form on the Lie algebra. Lie algebra is not the same as the space on which it is acting, right? That will be a particular representation. So the Lie algebra, which is basically like SO4, I mean SO3, 1, but it's essentially at the level of complexified Lie algebra, is the same as SO4 Lie algebra. So SO4 Lie algebra is a 6-dimensional space. So this is some form on this rotation, SO4, SO3, 1 rotations, right? Now this rotations thing is acting on, rotation group is acting on the 4-dimensional space. Right? So the metric you're talking about is a metric on the 4-dimensional space, the Lorentz metric usually, right?
So I mean, this Cartan killing form metric is defined on the space of, generator manifold.
Yes. So it's a vector space again, because we are talking about the infinitesimal generator, so that's a vector space, not the group manifold itself. Group manifold is a curved space in general. But here we're just talking about the Lie algebra, which is the infinitesimal generator, so that's a vector space. Okay, so it has nothing to do with the way for example, the rotation group appears in physics is to say that, okay, there is some, say, n-dimensional space where I choose some Euclidean metric. Let's take Euclidean example. And then you say, okay, what is the symmetry group which preserves this metric? Right? And that gives you the ON or SON, depending on whether you want to preserve the orientation or not. So let's say SON group. So SON group is acting on this n-dimensional space, right? So the metric which appeared in the n-dimensional space was the, say, identity matrix, right? But now Cartan killing form is on the SON's Lie algebra, right? Which is a dimension n times n minus 1 over 2, which is not the same as the original dimension, right? On the space in which it's acting. Yeah.
I have a question from last lecture. We said that if you choose the basis in which we put the Cartan elements first and the just odd positions, and then we list the x alphas, then the adjoint H will be block diagonal. I don't see why.
Block diagonal?
Yeah.
I mean, because anyway, by definition, so you're looking at the add H. Add H has what form? So you're asking why add H is block form? Okay. So add H acting on any x will be simply given by hx, right? Okay. Now there are two possibilities. So suppose if x belongs to, so let me call the Cartan, I think I was calling Cartan subalgebra as H, right? As C. So suppose if x belongs to C, of course this is 0. H with such x is 0. So this is equal to 0 if x belongs to C. Right? Now, if x is one of the roots, say x alpha, then this is alpha H, right? So now you take the space, and choose a basis in which, say, the top, the first one is C. It doesn't matter which one, but so choose a basis where these are the basis for the C. Suppose C is some k dimensional, then there will be k such vectors. And then choose the basis for the alpha root, alpha 1 root, alpha 2 root, whatever, the number of roots. Say there are k different roots, alpha k. At the moment we don't know whether it's one dimensional or not. But whatever the dimension is, okay, there will be, suppose this is 3 dimensional, then there will be 3 such vectors, and so on and so forth. But on each of them, what is the add H action? You see, add H action is just, here it is 0. So when add H acts on it, it gives you 0. So that means when I write as a matrix, so there will be blocks here, right? So this is in the same C, alpha 1, alpha 2, etc. And here is C, alpha 1, alpha 2, etc. In these blocks. So here it will be all 0. Right? Because when H acts on any of these guys, it gives you 0. So everything is 0 here. 0, 0, 0, everything is 0. Right? Now look at when add H acts on this space, which means of the type X alpha 1. It is going to give me alpha 1 of H here times identity matrix. Suppose this was 3-dimensional, then there will be a 3 by identity matrix, 3 by 3 identity matrix, right? And everything else 0, because the right hand side is again, this times X alpha, right? So right hand side, when it acts on X alpha, it gives you back again X alpha, right? So that's why it's diagonal here. And everything else 0, here it will become alpha 2H, again whatever the dimensionality of that space is, and so on and so forth. So that's the... Yeah, maybe we'll come back to this question that you asked towards the end of this chapter. We will postpone that for the moment. Although, as I said, we will not be discussing at all the abelian. We'll be talking about semi-simple algebras, right? Abelian algebras are not semi-simple. So the algebras we are talking about will be the ones where Cartan killing form will not be 0. It will be non-singular actually. So actually now let me just continue with did I want to read it? It's chapter 12. So first of all, I will start with some definitions. So definition 1. That so if a Lie algebra G has if G has no ideal, no what I should say proper ideal. Proper meaning is smaller than G. Not equal to G.
G is the ideal of itself.
G is it?
G is the ideal of itself.
G is an ideal because that's a trivial issue.
But therefore not a proper.
Yeah, exactly. So maybe I should just write either proper or non-trivial, because there are two trivial ideals. No, one is the Lie algebra itself, and the other is the 0 null set. So some non-trivial ideal. So which means let's say this is let's say call it H, such that H is contained in G. It's really smaller than G. How shall I put it? It is not equal to G. It's smaller than G. And also it is bigger than is not a null set. H is not a null set. I don't know, how shall I call it? Null set. H is not equal to null set. So something in between. And so there is no proper ideal H, then G is called simple. Called simple algebra. Okay, this is a definition. So in some sense, when you don't have anything, I mean, you cannot. That's it. I mean, it's a you cannot kind of take some smaller set. No. So this is simple algebras. Okay. Then, so for example, you see SU2 and SU3. Both of them are examples of that, right? Because in SU3 you cannot find any ideal, which is any non-trivial proper ideal. Because, okay, for example, if I look at the one-dimensional algebra generated by sigma 3, right? This is a sub-algebra of SU2. Right? SU2 is generated by sigma 1, sigma 2, and sigma 3. But now suppose I just take sigma 3, right? And consider all the elements of the type any number times sigma 3, and let me call this as H. C is because it has to be vector space, right? I mean, anything which is generated by sigma 3. So it's one dimensional. Any number times sigma 3. Now this is a sub-algebra of SU2, that is true, right? But it is not a proper, it's not an ideal. Because sigma 3 with sigma 1 or sigma 2 is not something which is inside the H. It gives you back up to some number, sigma 2 or sigma 1, right? Up to some numbers. Remember the definition of ideal was that if H is an ideal, then the H with the G is in H. Right? Is contained in H, yeah. For all the elements of G, yeah. I mean, if it was not this, if it was just G, then of course that's just a definition of a subalgebra. No, I mean, this is fine. This is automatically true. H with H will be in H, right? That is the definition of subalgebra. Okay. This is always true, of course, because anyway, H is contained in G, so this is true, right? But what is the additional condition on the ideal is that H with anything is in H. Okay. This is stronger. So up to now, this is just a subalgebra. This is just a definition of subalgebra. Right? But if that subalgebra also satisfies this condition, then you say it is an ideal. H is an ideal. This is a very strong condition. You see, we are saying that anything in G, when you take the commutation with the H, it gives you back H, not the G, right? H. It's a very, very strong condition. So clearly this is not sigma 3. So there you can convince yourself there is no invariant subalgebra, proper invariant subalgebra here. And the same thing you can show for also SU3. Okay. There is no proper. I mean, for example, if I take the x plus minus alpha 1 and h1, this is an SU2 subalgebra of SU3, right? In this picture. You have alpha 1 minus alpha 1 and h1. That forms one SU2 subalgebra of the full SU3. Right? But this is not invariant subalgebra. Okay. I mean, when you take the commutation relations of this with the remaining guys, x plus minus alpha 2, x plus minus alpha 3, and h2, this is not going to give you back the same elements. If you take commutation relation between one of these guys and one of these guys, it's not always going to come back to the SU2. No? For example, what was that? This we said x alpha 2, this was alpha 2. If I take x alpha 1 with x alpha 2, we get x alpha 3, right? Which is not contained inside here. So there will be no. So these are examples of simple algebras. And actually, we will later on study all the simple algebras, all the possible simple algebras. But at the moment, I'm just giving some example here. Now, let's go to more. The next definition is definition 12.2. That's a definition of a semi-simple algebra. So a semi-simple algebra I mean, an algebra is called, so G is called a semi-simple algebra, called semi-simple algebra, if Cartan-Killing form is non-degenerate. Is non-degenerate. So the B determinant of B is not equal to 0. B is the Cartan-Killing form.
Can you say that semi-simple algebra is the one which is a direct sum of simple?
Yeah. Yes.
These definitions are equivalent.
Yeah, one can prove all these statements. I'm not going to give the proofs of these things, but that is true. Every semi-simple algebra can be written as direct sums of simple algebras. That is true. In fact, that will be the one of the theorems which we just state without problem.
So the two definitions are related?
Hmm?
The definitions are related?
Repeat that again?
The two definitions for simple algebra and semi-simple are related to each other?
No. That is simple. This is semi-simple. There are two different things.
So I have an algebra which is simple and semi-simple? Because I don't see what is the contradiction. It's a sample.
Here there is no, I'm not saying anything about the ideal. It may have ideals. Right? Here we are saying there is no ideal. No proper ideal. I mean, no smaller ideal than that. Here it can have. For example, SU2 plus SU3. Direct sum of SU2 and SU3 is not simple, but is semi-simple.
Can we find Cartan-Killing form on simple algebra?
Yeah.
So, it can happen that they are non-degenerate on simple algebra.
On simple algebras, it's always non-degenerate.
It's always non-degenerate. So according to that definition, simple algebras are also semi-simple.
Okay, yeah, I mean, simple, what did you say? Yeah, sure. No, I mean, simple algebra is, I mean, I don't know whether, maybe, I should exclude from here U1. Because, let's see if, I must exclude U1 from this. Okay, because U1 is a bit of a problematic thing. Because, let me see, simple algebra, I mean, it satisfies, right? U1 has no, I mean, it satisfies this definition, right? It has no proper ideal. I mean, proper, it's already one dimension. So what can it be? Smaller than that will be 0 dimension, but that's also trivial. So that this definition is there, and this satisfies, but U1 is not a simple algebra. So excluding U1. So any other algebra, so not U1, but anything else which has no ideal, no proper ideal, is simple.
Why do we exclude it?
No, so in this definition, I have to say explicitly that not excluding U1, because U1 satisfies this condition.
Why not? Because the determinant of B is 0.
Yeah, determinant of B is 0. It's not a simple algebra. I mean, it's
Then they show valid for the definition that it has to be with determinant different from 0.
No, that is not enough, because determinant B not equal to 0 is also that.
Oh.
But this is not simple algebra.
Okay.
So we need that ideal. So in a sense, I mean, okay, what will happen is that every simple algebra is also a semi-simple algebra in the sense that the Cartan-Killing form is non-degenerate. Yeah? But it's more than that. It is that it has no proper ideal. Whereas here, I mean, so this kind of things are not included.
So we can say that a simple algebras are semi-simple with non-trivial ideals. simple algebras are semi-simple algebras with a non-trivial.
Yeah. With no non-trivial ideas, right?
So actually, in some sense, the second definition should come first, and then the first definition
Yeah.
is defined in terms of that.
Yeah.
Because I had in mind that the algebra is either sample or the same sample. I didn't know that we can have some intersection between the two. Maybe an algebra is sample and semi-sample at the same time.
Yeah, I mean, so basically from this what we are going to say, okay, why don't we wait until the theorem? The theorem which relates the semi-simple and simple.
So
Okay.
is U1 the only exception for the definition of simple? Is the only one that you should exclude?
U1.
How do you know that there are no other things that satisfy this definition but actually have the...
No, you can prove, I mean, you can prove that if you have no, I mean, let me just come to the next statement. The next statement becomes clear completely.
Yes.
So the next definition, you see, normally, this is not the way people define, mathematicians define semi-simple algebras. So the way they define semi-simple algebra, which is actually turns out to be equivalent to this. These two things are equivalent. But one needs to prove it. I'm not going to give the proof of this, but anyway, this definition is what mathematicians usually use for semi-simple. So they say that semi-simple algebra, semi-simple algebra is something, is an algebra which has no, is an algebra which has no abelian invariant or ideal, abelian ideal. This is how one mathematicians usually define it. Which has no abelian ideal. Okay. So it may have ideals, but the thing is that it should not have an abelian ideal.
So, are you talking about proper ideals only?
Yeah, I mean, actually, not even proper. I mean, if it was not proper, if it was itself, then then it would be just an abelian algebra.
So it automatically excludes U1.
Yeah, it's not. I mean, it could be. You see, for example, not just U1 to the n. Let's say I can take anything. Right? So it's they will. Yeah. So that's the statement. Now, it turns out that these two statements are equivalent. It's meaning if you one can I mean, so one can prove, for example, that if this has an abelian ideal, then one way of proving is easy. So from here you can prove that. Other also its proof exists, but it's a little bit more complicated. Okay. So just to give you an idea, although it's not included in the notes, just to show how, I think we already discussed that before. So suppose H is an abelian ideal. H is inside G, and H is an abelian. First of all, let's just call it ideal. First, then we'll impose further the condition that it's abelian. So step by step, let's do that. So this is an ideal. So let's choose a basis. So what does it mean? It of course means, it implies that H with G is in H. Right? That's what it means. So again, let's choose a basis where, say, the top guys are the basis for the H, and the remaining ones here. So for example, if this is a n-dimensional and that's m-dimensional, where m is less than n, then you have m here and the remaining n minus m. So choose a basis in this way.
The idea is something like you are going to prove that two rows are same, then the determinacy of the B matrix.
I mean, I think we have already discussed this before. So what happens then? So if I now take, so let's take add H, add of some element, let's say H, let's say where H belongs to capital H. So it's in the ideal. So how it's going to act on this space? H with H will be contained in H. That is, of course, because it's a subalgebra anyway, right? So in this block, so the commutator of H with any of these guys will be inside here. So this will be non-zero, right? But now add H with the remaining guys is also going to be inside the H. That's what this statement is saying, right? So here, and this part will be all zero, right?
You will have 0 rows therefore.
Yeah, exactly. But so far, no. At the moment, since it is still, I'm talking about ideal, it will be this. That doesn't mean that this is degenerate, right? But now we impose further the condition that this actually is abelian. That means this part is 0, right? Because the commutator of this with any of these guys is going to be 0.
Actually, you have to take the element of a trace, so
That's right. Yeah. Okay. So, is that clear? I mean, if it was just an abelian, just an ideal without no, it's not abelian. In that case, it would be something here because the commutator of this with any other element is not 0. It's not abelian, right? It will give you back something inside H, right? So it's not in general 0, right? So in this situation, there is no problem. I mean, in general, the Cartan killing form will not be 0 in this case. Huh? But if it is this abelian, this ideal happens to be also abelian, then this becomes 0. Because these are nothing else but the structure constants within the Lie algebra H, subalgebra H, right? Because this H, if I choose some basis, say HI, then any other element HI with a J commutator will be some Fijk, Fk. Right? So here this will be just Fij case. Right? But if it is abelian, then these are 0, so everything becomes 0. Here, not that there, but this becomes 0. And then if I take now the B of say H with H prime, H prime is another element of this H, then you see that here it just vanishes completely, right? So one way you can prove more easily that if it has a abelian ideal, then the Cartan killing form is degenerate. Okay. The other way to prove is a bit more complicated. So to prove that, I mean, if Cartan killing form is degenerate, then that algebra has a non-trivial abelian ideal. Huh? That's a bit difficult to prove, but roughly the way it proceeds, I mean, I just kind of give you an idea how one might try to prove it, but there are some subtleties there, so that's why. I mean, if I look at, let's consider, let's see how to say this. Yeah, I mean, if the Cartan killing form is degenerate, what does it mean? That there exists X belonging to G such that B of X, Y equal to 0 for all Y belonging to G. Correct? So at least one X must exist. I mean, non-trivial X. Not, of course, you could take 0. Then it's a non-trivial X. So now consider the set of all X's, all such X's, such that B of XY equal to 0 for all Y belonging to H. Okay. Then, first of all, you see this subset. Let's call it something. Give it a name. Let's call it H. H is the set of all X's such that BXY, all X belonging to G, of course, which satisfy this condition that this B of X with any Y equal to 0. Okay. Then you see the two things you can see, that this is a vector space. This H is a vector space. Because if x1 and x2 belong to H, right, then clearly x1 plus x2 also belongs to H. Right? Because, so x1, x2 belongs to H means B of x1, y equal to 0 for any y, B of x2y equal to 0 for any y. So clearly any number a plus b x2, ax1 plus bx2 also belongs to. So it's a vector space structure. What about the commutator? So what I want to show is that this is a subalgebra. This is an algebra itself. So the commutator x1, x2, if I take these guys. So let's look at this. So question is, there's a question mark, does it belong to H? Okay. So to check that if it belongs to H, it must satisfy this condition. So we want to check this, right? If this is 0 or not. That's what we want to check. Because if this is 0 for all y, then clearly the commutator x1, x2 also belongs to the set H. Yeah? Actually, not even that. So let's see. So what is the B of? So this is nothing else but the trace of add. So we are looking at the add of commutator xy time x1, x2. Sorry, x1, x2 with add y. Right. But add x1, add x. This one is the same because as add x1, add x2 commutator, right? And then you still have the trace and y. But this is two terms, right? Add x1, add x2. So let me just open it up. This commutator. This minus add x2, add x1. This whole thing times add xy, add y, right? Now the second term, what I can do, I can use cyclicity property, right? So I move this add x2 on the other side. In the trace, I can always, there is cyclic. So this I can write it as trace of add x1 with the commutator of add x2 and y. Okay. And then this I can rewrite it as b of x1 comma commutator x2y. So this is a general statement. It's not just for this. So what we are saying is that this we started with this b of x1, x2, y. Okay, that is the same as by using just the cyclicity. One is just using the cyclicity in the definition. You can always move the commutator. This is in general true. But now in this particular case, what happens is that after all, for any y, x2y it will be some element of G, right? But x1 by definition, when we said x1 belongs to H, meant that the b of x1 with any element of G is 0. Therefore, this is also 0, right? But that means x1, commutator of x1, x2 also belongs to that set, because this is true for all y, right? So therefore, this is a subalgebra. In fact, you can now just, but we want to check whether this is an ideal or not. That means we want to check so that's subalgebra. But now next step is to check if it's an ideal. Okay, so the next step is to ask whether H is an ideal. And that again, so what we wants to check is whether HG is in G, is in H. That's what the question mark. That's what we want to check. So take any element of H, let's say X belongs to H, and some Y belonging to G. Okay. Now I take the commutator, so we want to check whether X, Y also belongs to H or not. So which means basically I need to check whether this with any Z equal to 0 for all Z belonging to G. That's what we want to check, the question mark. If you can show that it is 0, then that means this commutator is inside H. Right? And that again is the same procedure because, as we said, that statement from going from here to there was general, right? Where we just use it cyclicity. So this B, this is the same as B of X commuted with Y, Z. Or maybe minus of that. No, it's okay. Y, Z. But then 0 because this is anyway contained in G and that is in H and we have the, since that belongs to H, X with anything is 0. So this is 0. This is correct. Now that means this is an ideal. Yeah.
How do you should define the simple algebra as that has no non-abelian ideal? Because if it has an abelian ideal, we can say that any simple algebra is semi-simple. Not only for U1.
Now repeat it again.
I said that we can define simple algebra by saying that if G has no non-abelian ideal. So G is simple.
No non-abelian ideal.
No non-abelian ideal.
Yeah, you could say that. Yeah. You could say
So
that.
in general, we
In
don't
general, yeah.
just
I mean, that's what will happen. Yes, yeah. Okay.
How do you prove that this ideal is abelian?
No, that you don't prove. I mean, there are. I mean, it's a bit. That's why that's the difficult part here. At the moment, we cannot show it, but it turns out that even if it is not abelian, you can start writing down a chain of things: H, H1, H2, and so on, sequence of things, where H1 is obtained. I mean, after all, if you take H commutated with the H, it is certainly contained in H. No, it's contained in H. It may be equal to H, but it may be also smaller than H, right? So this H1 is that. Then you take H2, which is the commutator of H1 with H1 and so on. Okay. So then there is a way to prove that the sequence eventually will end to the null set. Okay. So the last one, whatever that say suppose the nth term, then finally gives you 0. That means this is abelian, and this will all be. So there is that's why it's a bit more tricky. So I'm not giving the proof of that. But I just give you a kind of hint. I mean the idea, how one can start by looking at the kind of all the sets, all the x's which have this property, which is what we call H. This subset, this subalgebra H, and that this is an abelian, and this is an ideal, and then from there you can show that there exists an abelian ideal. So that's a little more tricky. But this is a fact. I mean, this is a kind of both statements are equivalent. Both definitions were equivalent, completely equivalent. Either you define it as saying that the Cartan-Killing form is non-degenerate, or you define it as they're completely equivalent, or that it has no abelian ideal. Both are equivalent. As I said, usually mathematicians define the way by saying that it has no abelian ideal, and then from there they prove that means the Cartan-Killing form is non-degenerate. But for us, we'll just use both of them interchangeably. Okay. So, and then finally there's a theorem which basically says that any semi-simple algebra, is equal to the direct sum of simple algebras. Sorry?
Many times this is written as a definition of semi-simple algebra.
Yeah, but that, I mean, well, okay, yeah, you could use that as another definition. But I think, okay, it's, I mean, how to say, you could use it, but I mean, I think it's much more powerful to say the statement. This is, of course, one can use the definition, but it's I mean, it's not guaranteed that if there is an algebra which is where the Cartan-Killing form is non-degenerate, then it necessarily can be written in this way. That one has to prove, right?
So this definition does not imply the other two definitions.
No, of course, I mean, once you write this, then since in each of these simple algebras, Cartan-Killing form is not degenerate, then also the direct sum is not degenerate, right? But to say other way around, that anything which has a B is non-degenerate implies that it can be written as a direct sum of simple algebras. That is not obvious, right? So there is a lot of work required to prove that actually.
Because if the B is non-degenerate, it can be a simple algebra as well.
It can be simple algebra also, yeah. But that any algebra which has B non-degenerate can be expressed as direct sum of simple algebras. That requires some proof. I mean, not obvious, right? So this actually is very exhaustive then. When one is saying that take any non-degenerate Cartan-Killing form, there is necessarily a direct sum of simple algebras, and therefore it is sufficient to study simple algebras. You know, and you can understand then all the semi-simple algebras. All right. So with this, these are kind of statements that we are not giving the proof in these notes. Okay. Now let's go to the. So we'll be focusing on the semi-simple algebras for the time being, and later on to simple algebras. So we'll assume right from the beginning the Cartan-Killing form is non-degenerate. So we assume this is non-degenerate. Okay. Now, so the next step is, as we saw it both in SU2 and SU3, is to start defining the Cartan subspace, right? So that is defined Cartan subalgebra. So yeah, so there is this Cartan subalgebra, which is usually defined, which we say is a maximal abelian subalgebra. Is a maximal abelian subalgebra. And so, like as we saw an example of SU3, we had what we called H1 and H2, right? This was the maximal. Once you have chosen this, then to this I cannot add anything else. No, I mean any other generator I cannot add, because then it will no longer be abelian. Yeah, that was what we said. So it's a maximal abelian subalgebra, and then what we can do is, as usual, we can write the algebra in terms of the root spaces. Right? So roots are alpha, which is such that H commuted with any x alpha is alpha H with x. The root spaces. There's a little technical thing which requires, I mean, these things are not, I mean, there are a lot of steps which I mean, you know, it's not so obvious, all of these things. For SU2 and SU3, I mean, if you give me an explicit matrix algebra, then of course one can construct. But here now we are discussing completely generally. There is no matrix in sight, I mean, just completely general. So, in such cases, one has to be a little bit more cautious. First of all, you want how to define a Cartan subalgebra. Okay. So I'm just giving. We will not be needing it, but I just for completeness, I will just say something here that there's a notion of a regular element. There is a concept of regular element. Okay. And a regular element is defined, say H, suppose H is a regular element, then it should have the property that its adjoint of H has minimal number of zero eigenvalues. Minimum number of zero eigenvalues. Okay. This is to avoid, you see, it is, just to give you an example, let's say, go back to SU3. Let's say I have this alpha 1, alpha 2, alpha 3, right? And H1 and H2. And the minus alpha 1s. I could have chosen, instead of starting from this as a Cartan subalgebra, H1 and H2, define the Cartan subalgebra. I could have started with something else. I could have started with, say, for example, alpha 1, x alpha 1. Okay. X alpha 1 I could start with. Then I would get a totally different Cartan subalgebra. Now notice that x alpha 1 is what are the zero eigenvalues of add x alpha 1? Add x alpha 1 computes with alpha 3. X alpha 3. So x alpha 3 will be one of the will give you zero eigenvalue. X alpha 1 with x alpha 3 is 0, right? And x alpha 1 with x alpha 1 of course itself is 0. And finally x alpha 1 with that combination lambda 8, which is a certain combination of H1 and H2, is also 0. So you see it has 3 zero eigenvalues as opposed to H1 and H2. So that's the point. If I chose, so if you start with the, if I had just, of course it's completely unnatural to start with x alpha 1 when you have the matrices explicitly given there, 3 by 3 matrices for all of these objects, right? But say somebody just comes and just say, okay, I'll start with this, and then I start considering the maximal commuting subalgebra starting from x alpha 1. Okay. What commutes with it? I could choose then x alpha 1 and, for example, lambda 8 as my Cartan subalgebra, right? If I choose lambda 8, then I cannot put x alpha 3 because lambda 8 does not commute with x alpha 3. Or I could have chosen x alpha 1 and x alpha 3, right? But that neither of them will give you anything interesting. It will be all a mess. You will not learn anything from that. Cartan subalgebra. Okay. So to avoid this pathological situation, one has to make some assumption that you see. That there is a the regular element. Where was I? Where did I define here? Regular element is defined as that. So from this point of view, x alpha 1 is not a regular element, right? X alpha 1 is not a regular element because it has 3 zero eigenvalues. Okay. But H1 and H2 are H1 and H2 have H1 has the only thing which commutes to H1 is with H2 and itself. So it has only these 2 zero eigenvalues, right? Whereas x alpha 1 has 3 zero eigenvalues. So x alpha 1 is not a regular element. So you choose H1. Another example of something which has which is not a regular element is what we call lambda 8. You see, lambda 8 is not, even though it's diagonal, lambda 8 went like this, no? Something like 1, 1, minus 2. Some normalization factor, but important point is this, lambda 8. If you look at this, of course it commutes with H1. With the Cartan subalgebra itself, because this is a combination of H1 and H2, so it's part of the Cartan subalgebra, the usual Cartan subalgebra we talk about. So it of course commutes with the Cartan subalgebra, so that is 2, but also it commutes with x plus minus alpha 1. It commutes with all of them. Why? Because x alpha 1 was this here, right? 0, 1, 0, 0, 0, 0, 0, 0, 0. You see, because this block, this is identity, right? So it's going to commute. with both plus alpha 1 or minus alpha 1. So this element has 4 zero eigenvalues. It's not a regular element.
That's why it's not right. Also it's right.
Others are okay. So H1 and H2 are fine. But just lambda A, because there is a block which is identity. Block, a 2 by 2 block which is identity. Or you could have chosen another combination which makes this, let's say minus 2, 1, 1. Again, this is another combination, right? This again will have eigenvalue 4. I mean, the eigenvalue equal to 0 will have 4 zero eigenvalues, right? You see, I mean, in this case it will be, it will commute with alpha 2, x alpha 2, x plus minus alpha 2. And similarly, so to avoid this kind of pathological situation, so what one says, the correct definition of Cartan subalgebra is, it is a maximal abelian subalgebra which contains at least one regular element, okay, which contains at least one regular element. That's the
We can't have the regular element outside the carton. We can't have it outside.
We can have what?
We can't have the regular element outside the carton.
No, regular element is just defined in general. I mean, I mean, I don't know. That is not necessarily true. I don't think that is necessarily true.
Probably we can have 2 regular elements. One is making another Cartan subalgebra.
That's right. That's right.
But in this case, you will have the same number of zero eigenvalues. What I mean, suppose outside the Cartan subalgebra we have a regular element which has the minimum compared to all the elements in the Cartan subalgebra. So maybe, for example, it's outside the Cartan subalgebra and it has 5 zero eigenvalues, but the one in the Cartan has 4, for example. Can it
No. I mean, so all it's saying is that there should be at least one element in the Cartan subalgebra which has a minimal number of zero eigenvalues, right? Then you start considering all the set of generators which commute with it and with each other to construct the full Cartan subalgebra.
But there can be more than one regular element which can generate
Different Cartan subalgebra. Take SU2 itself, right?
Actually.
Why? We just use sigma 3 as my Cartan, right? You could have chosen sigma 2 or sigma 1. It doesn't matter, right? So, I mean, there are many different choices of Cartan subalgebras. Okay, this is just a technicality. As we said, for matrices we obviously are going to choose some diagonal generators, for simplicity. That's even simple to work with. So that's the technical thing. Okay. So with this now, okay, there are a few theorems here, and I'll start going through the proofs of that theorems now. So at the end of this chapter, we'll see that all the structures that we had for the SU3, the roots and the commutation relations, the kind of things we have obtained, but that we obtained just by inspecting the SU3 matrices. We had the SU3 matrices, right? But now what we'll prove is that this is a general statement for any semi-simple algebra. The similar structures, that there are lots of SU2 subalgebras, right? Each non-zero root defines an SU2 subalgebra. All of these features that we found in SU3, right? That's a general feature for any semi-simple algebra. That is the aim of this next set of theorems. So first statement is, so this theorem 12.3. It has several statements. One, that the full Lie algebra G is the Cartan. So Cartan we will define as usual with the H. So H is a Cartan. Is the Cartan subalgebra. Subalgebra of G. Okay. So G can be written as the level of vector space. It can be written as H, sum of H plus alpha belonging to the roots delta G alpha. G alpha. So what does it mean here? It just means that once I have the Cartan subalgebra, then I can, once I've defined my Cartan subalgebra, I can start constructing the eigenstates of the add H, where H belongs to H, which acting on, and then you can find the eigenfunctions, eigenvalues, right? Because this is a maximal commuting set, so you can simultaneously diagonalize all of them. Okay. So add H x equal to alpha H x alpha. So you set, and this can be done for all H's simultaneously because this is a max commuting subalgebra. Okay.
You have written x of alpha as g of alpha there.
Yeah, so G alpha. So what is the idea? So, I mean, but it's not guaranteed, right? I mean, maybe that there is not just one X alpha. This eigenfunction could be degenerate. I mean, multiple eigenfunctions, no? You have an eigenvalue alpha H. But it could be that there are more that there are more than one eigenstate, linearly independent eigenstates with the same eigenvalue, right? That could happen. In SU3 it doesn't happen, but now we are discussing generally, no? So it could happen in general. So that's why. So this G alpha is the subspace of eigenfunctions with the same eigenvalue. Well, it will turn out finally that this all have dimension 1, but a priori we don't know.
Generally, in all the groups, generally.
For all the semi-simple, yeah.
So the summation sign that you have used is actually the summation for direct product. The summation sign in front of G of alpha, it means that the direct product of all the subspaces.
Yeah, I mean this is what I call direct sum. Direct sum. This is as a vector space. I mean, it's not as an algebra, vector space. Because I mean, these are not subalgebras. I mean, this is subalgebra, but this is not a subalgebra. Right? So this as a vector space, I'm writing it as a direct sum. I mean, this is not a this is not decomposition of, because this doesn't commute with that, of course, right? So it's not a, it's not a direct sum of algebras. The direct sum of vector spaces.
For subspaces of G, you can say that.
The vector space of G is, I can write it in this way. So this is just a standard, I mean, eigenfunction decomposition, right? So you write, you have, I mean, suppose that there was only, it's one dimensional, H was one dimensional. You have just one Cartan subalgebra generator, I mean, independent Cartan subalgebra. Then I just look at that generator and just split the whole space, G space, in terms of its eigenfunctions. No? So then if G is n-dimensional, then I should find n eigenfunctions. No? But some of them may be degenerate. Some eigenvalues may be degenerate. So it could have higher dimension. No? So that's okay. So the first statement is just that. So you just, I mean, you can always write that, write this G in terms of this combination, in these sums, in the direct sum of the vector spaces.
So you're going to show later that they are not degenerate for semi-simple algebras.
Yeah, we'll show that.
Okay.
Yeah. I mean, that will be the whole set of theorems, one after other. Okay. Now, this chapter is full of theorems too. So, yeah. I mean, okay, it is just that, I mean, some of the theorems we are not proving, some of the theorems we are proving. But it's good for you to see the proof because, it gives you an idea how these things are working. Some of the proofs at least. Some of the proofs which are not too complicated.
And actually, we also show that the limitation of that, in which circumstances this theorem is correct.
Yeah. Right. Okay. So this is more or less the trivial statement. I mean, trivial statement that once you have maximally commuting set, I mean, there are some subtleties here, but I will not mention the subtleties here. I mean, it will just be confusing. Okay. So, I mean, it has to do with that this general statement that you can find eigenfunctions, but it doesn't necessarily mean that you can diagonalize. Eigenvalues you can find by just the usual equation, determinant of the matrix minus lambda times identity matrix equal to 0. It gives you a polynomial equation for lambda. You can solve, so you get n roots, n solutions for the lambda, but it's not always true that you can diagonalize all of them. Okay? You know that, I mean, you know this statement, right? The best you can do is, given any matrix, the best you can do is to bring it to a canonical Jordan form. No? Not always is possible to make it completely diagonal.
Because, can you say that this is because suppose that you have two different eigenfunctions which are dependent, and then the diagonalization matrix does not have an inverse.
Well, I mean, it's the following. It's something like this. Okay. I mean, I shouldn't spend time on this now, but okay. Since you raised this, just quickly say that. I mean, take a simple example. Suppose that you take a 2 by 2 matrix which is of the form, say 1, 1, and x. X is not 0. This is 0.
Shear matrix.
Huh?
Or the shear matrix, probably.
Is what's called?
It defines the transformation of shear transformation.
Shear transformation. Ah, okay. I didn't know. Okay. So the question is whether I can diagonalize it. Answer is you cannot diagonalize it. Because, I mean, if you look at the eigenvalues, let's look at the eigenvalues. Eigenvalue equation, so I have to look at dit times minus lambda times the identity, right? I have to look at that.
1.
So it's 1, of course. So I mean, just to write it explicitly, 1 minus lambda x, 1 minus lambda 0, right? So determinant of this gives you 1 minus lambda square. So lambda is equal to 1. So both the things. Now try to construct. Let's say I try to construct 1x0, 1, and let's say I want to find the eigenfunctions with eigenvalue 1. Okay. So you find, so the first equation gives me a plus xb equal to a, and second equation just gives me b equal to b, but that tells me that, I'm assuming that x is not 0, that b has to be 0, right? Then we are finding only one eigenfunction. I mean, one independent eigenfunction, not the second. Because its multiplicity is 2. So I should find 2 eigenfunctions, right? I could find one, and that's it. There is no other possibility because b has to be 0.
So you cannot construct a diagonalization matrix for this.
That's right. Yeah. But what you can do is, I mean, you can find what is called a generalized eigenfunctions. And there's a whole theory about generalized eigenfunctions. Okay, so that happens. I mean, it's clear that this problem is happening because it's degenerate. There are 2 states with the same eigenvalue. If the eigenvalues are all different, if this was not 1 but something else, let's say 2, okay, then it will be lambda 1 minus 2 minus lambda, and then there's no problem. You have lambda equal to 1, lambda equal to 2 solutions, and in that case you can really diagonalize. You can find 2 different eigenfunctions. Right? But here's a very peculiar thing that happens, that the 2 eigenvalues are equal, and in that case it's not guaranteed that you can diagonalize. In this matrix you cannot diagonalize as it is. But this is what is called the Jordan form, canonical Jordan form. You can always bring it to this form. So for these theorems, I mean, we can just generalize it and say that these are not necessarily eigenfunctions, but generalized eigenfunctions. So generalized eigenfunctions are defined like this. So let's say some matrix M, and I have some, let's say some eigenvalue lambda which appears n times, which is a degeneracy of n times the same lambda appears, right? Then what you can do is you can write lambda times identity to the power of n equal to acting on some state equal to 0, and you can find the states. Then here you can find all the n eigenstates. But this doesn't mean that. So what happens is that you start with something which satisfies this psi equal to 0. But you're guaranteed to find only one such state. It could happen that you find everything, but what is guaranteed is that you will find one such state. Like here this was one state, right, which we found. But then you can start constructing other states which are kind of not this, but say m minus lambda I square acting on some psi 1 equal to 0 and so on. So these are kind of generalized. But this problem will not appear for us because finally we'll show that these are all dimension 1 spaces. Huh? So there's no problem like this. Huh? Okay. But at this stage we are just saying that we construct all even if it's generalized eigenfunctions, we put all the generalized guys in this space. So, please don't, this is just an unnecessary complication. This situation doesn't arise for us. So. Okay, that's one. Second, these are all we have already done, so I'll go very quickly. If beta belongs to delta, delta is a set of all eigenvalues. And then, of course, G alpha, G beta is contained in G alpha plus beta. This is we have seen it again and again by just to look at apply add h on both sides, right? And then use the Jacobi aridity. Then here you get the sum of alpha h plus beta h. So that is what this you have seen many times, right? Please. We have done it many times, right? So this is clear, right? Or is there any question to anyone? Okay. So this is obvious. And then the third state.
That alpha plus beta should also be in the root.
Yes.
Well, if it is not, then this would be null space. So then, of course, then it will be 0. Yeah.
No, alpha plus beta, should that be in the root set?
Yeah. Suppose alpha plus beta is not a root, then this would be a null system. Right? There will be no such thing in there. In that case, the commutator will be 0. Yeah. If alpha plus beta is does not belong to delta. Okay. Then the other thing was third, if alpha beta belongs to delta and alpha plus beta is not equal to 0, then this is an important point, and again this we have seen, G alpha, G beta is equal to 0. Right? Remember the proof, we have went through it, but very quickly I remind you what is the proof. So we saw that so this we have to add G beta. By this notation I mean any element of G beta and any element of G alpha. Yeah? So that's what I mean. Add G alpha, and then so let's add this, apply this add G beta on something which is say G gamma, some element of G gamma. Right? Then you already know from this that this guy will be in G beta plus gamma, right? And then I apply add G alpha on, so this part is that. Now I apply add G alpha on that, then I will get G alpha plus beta plus gamma. Now if alpha plus beta is not equal to 0, then you see this is not equal to gamma, right? So what we are saying is that in this case, G gamma is mapped to something which is some G gamma prime, where gamma prime is different from gamma, right? But here at the end I have to take the trace. This fact tells you that it's off diagonal, right? And since we are taking the trace, it will vanish. So that was the statement. So this will be 0 if it's not. So up to now it was more or less, we have seen it many times, but now let's look at this, the fourth statement, that Cartan killing form, so let's say B restricted to H is non-degenerate. Okay. B restricted to H is non-degenerate. So what does it mean? It means that if I choose a basis, what that means is that where I put, so the first guy is in H, first whatever the dimension is over the Cartan, and then the remaining ones, so the G alpha, G beta, etc. So I take this block form. Then if I restrict, so B will be some, in general, some, suppose the whole dimension is n, so it will be n by n matrix, right? But when you say I restrict to, meaning that I restrict to just this part, this block. And the statement is that even if I restrict, of course I know that the full determinant is, full B is non-degenerate, because we are assuming the semi-simple the algebra. This whole thing is for semi-simple the algebra. So therefore, this full the full determinant is not zero. That I know. But what we want to prove is that if I restrict to this Cartan subalgebra, which means the small block, that determinant also is not zero. So that's what one wants to show. Okay, so how is the proof goes? The proof basically is just simply going from here. I mean, if you look at this, it tells you that, so from this, it becomes immediately clear that, I mean, so let's look at all the blocks. So we have this kind of blocks here. Okay. But if I take the B of H with any G alpha is equal to 0 if alpha is not 0. If alpha is not 0. Right? From the same argument, because H has zero eigenvalue. Right? So it's like taking this thing where just setting beta equal to 0. If beta is 0 and alpha is not 0, then this will be 0. Right? Is that clear? Huh? So therefore, I mean, here all of these off diagonal guys have 0. Right? I mean, we said B of anything in H with any G alphas where alpha is not 0. So those are these ones. Right? That metric is 0. So therefore, the B matrix will have, so the first index, the row index is H, some element of H, and the column index is the G alpha, then that must be 0, right? So which is these blocks.
It means that in the Cartan block, it cannot be 0 because
that's right. So you see the determinant. So since this block is 0, the dit B, the full dit B, factorizes into dit B restricted one. I mean the B which is restricted to H, which is this part. This is something, and the rest of the determinant, B rest. No? So since this thing is not 0, therefore this also cannot be 0. That is the statement. Okay. Then what else? Right. Again, this we have gone through it, but in the case of SU3, but let's just do it again. So if the fifth statement is if alpha belongs to delta, then minus alpha also belongs to delta. So positive and negative root. And that again comes from the same thing. That now let's look at this here. I look at the G alpha. So B of G alpha with the G beta is equal to 0 if alpha plus beta is not equal to 0, right? So you see that the only way, if I look at this row, G alpha row, the only way any element can be non-zero is if beta is equal to minus alpha, right? So suppose there was no minus alpha at all. Suppose there was, for some alpha here, the alpha exists, but minus alpha does not exist. Okay, then that means this entire row will be 0. So, right, that part is clear, that the entire row will be 0, right? Because there is no, I mean, the only time this will be non-zero is if you have this beta is equal to minus alpha. That is the only possibility that this may be not 0, right? But if there is no minus alpha, that means everything is 0 in this row. Then the determinant will be 0. So that is just again the same. So you see that this Cartan filling form, non-degeneracy, how powerful it is. I mean, you are getting the structure out already. Then the root structure, that this is non-degenerate, that for every alpha there is a minus alpha. I mean, it's very, and we'll see how almost everything we can deduce from the non-degeneracy of this Cartan-Killing. And finally, yeah, this is again another interesting thing. So if I look at the set of all alpha belonging to delta, then this spans H star. H star is a dual to the Cartan subalgebra. Remember that we discussed the dual space, the roots are living in the dual space, right? So these alphas are living in the dual space, right? But what is not clear is that this would span. So remember in SU3, the Cartan subalgebra was two-dimensional, right? So roots were actually drawn in a two-dimensional plane because there's eigenvalue with respect to H1 and H2. So there are two parameters there, right? So you need to. So the Cartan subalgebra is two-dimensional. Dual vector space, which is the root space, was also two-dimensional in that case because remember we had this picture. So already, I mean, even forgetting about everything else, just take alpha 1 and alpha 2. This is already spanning the two-dimensional space, right? Because any vector can be written as, any point in the two-dimensional space can be written as x alpha 1 plus y alpha 2 for some arbitrary numbers x and y. So spanning means that, right?
So if you look at alpha 1 and alpha 2, the dimension of the roots is actually greater than or equal to the dimension in which they are living, and they are all not linearly independent, then it means that
that's right. So I mean, of course, there's alpha 3, but alpha 3 is not independent because I can write alpha 1 plus alpha 2.
For alpha 1 and alpha 2 to prove that they are linearly independent.
That's right, yeah. But now the statement is, how do I know that? SU3 we know it because we have explicitly the expressions for that, no? But how does one know, I mean, that in some more complicated algebra, that maybe which is again, Cartan subalgebra is two-dimensional, it could be that everything is alpha 1, alpha 2 are all in the same direction. Alpha 1 is this, alpha 2 is that, how do I know this? Huh? So that's the point. I mean, could be that all the roots are in this one-dimensional space. No? It could have happened, right? But the statement is that again, if algebra is semi-simple, then this, it cannot happen. Alpha spanned completely, the full space. So the way the proof goes is for this statement. So I mean, suppose that let's say so we prove it by contradictions, right? So assume that it does not span. Huh? So suppose it doesn't span. Suppose alpha belonging to delta does not span. Span H star. Then there must exist an H belonging to H such that for all alpha in the roots, alpha of H is 0. Okay. Because we are saying, because remember this was the dual space, so we have these are linear functions. So if you are saying that these alphas do not span all of the H star, right, then there must be some H for which all the alpha H is equal to 0. For all alpha. I've written already. For all alpha belonging to delta. The dual space is smaller. I mean, this is alphas are the smaller subspace of dual space, right? The full dual space. So there must be some H for which, some H belonging to the Cartan subalgebra, for which all the alpha H is equal to 0. But then you can, then compute the V of H with any element K. So for all K, so I choose this particular H. I take this particular H for which all the alpha H is 0. So I choose this particular H and I look at the Cartan-Killing form of this H with any k. So with any k in the Cartan subalgebra. Sorry, now I started calling this H. So there is a slight change in the notation. Before I was using Cartan subalgebra for C, but in this we are calling H. Okay. So I hope this doesn't create any confusion. So for any k in H, and that is simple because this we have already shown in one of the exercises, right? That exercise was completely general. That this you can always write it as sum alpha H, alpha k, where alpha belongs to all delta. Right? That yeah. And if alpha H is 0 for all alpha, then this will be 0. Right? This will be 0.
It means that V of H is degenerate.
Exactly. Because this is true for any k, because the k didn't enter. K could be arbitrary. But so long as I have found an H which satisfies this, then this will be 0. So which means that this will be, this part will be degenerate. Right? But that is not the case because we are assuming that it's semi-simple. So this is not degenerate, and therefore alpha belonging to delta must span the entire dual vector space. That's the idea. This is again. So you see that all this thing that we found in SU3, they are not accidental. In SU3 we did find that the alpha 1 and alpha 2 spans the full two-dimensional space, right? But it's not an accident. It is just a consequence of the fact that it is semi-simple. In that case, it's simple, but okay, it's a semi-simple. Okay, that is the first theorem. Now, let me see how far I can go. Okay. Any questions on this? I see if can I take some 10 minutes more? 10, 15 minutes more? Or your time? Because I mean, actually I was planning to finish the entire chapter and I just finished the first theorem. Oh. And we have only 3 more lectures next week.
And the date of the exam is going to change? So.
Date of the exam has been fixed, right? It was not the next week, the week after. The Friday, the week after. So you'll have 1 full week. And I think during that week also there will be a tutorial. So it will be useful because, during the weekend you'll start preparing and go through the whole thing, right? Then you may have many questions to discuss. It could be useful. So, what is the vote? Should I continue or not? Just this say 12.4, the theorem. Huh? Okay, if you are very tired, then we can stop. So it seems there is a general consensus. I'm really glad to see how much motivation the students have. Okay, good. So now we go through this. Remember that last lecture's discussion that given if the B is non-degenerate, then you can use this to give a map. Degenerate. We can use this to give a map between H star and H. Right? Because we have a good metric here, non-degenerate metric. So then we can give a one-to-one map between elements of H star and H. It's like what we discussed yesterday, raising or lowering indices, no? That analysis. So, and that is defined, it's simply, so we have given an alpha and k, which is a function of k, and which is acting on, so k belongs to H. And this is the dual vector space, so alpha acting on k will be some number, right? So alpha is an H star. So we can define a unique element which is given by BH alpha k. So we say that this is true. So we are mapping, so what we are doing is we are mapping alpha to H alpha. Alpha is an element of H star, H alpha is an element of Kaplan subalgebra. So we are giving a map, and that map is defined by this. So this such that H alpha is defined for that, this equation. This should be true for all K. For all K. Remember we did that, right? Yeah, yesterday we did that. I think this discussion, or day before yesterday. So we can give this map here, and this will be very useful. This will be very, very useful. Okay. I see that there's an exercise here. This exercise was one of the things which we used already. B of x, y, z is the same as B of x, y, z. Right? They're using cyclicity. This is an exercise actually. Okay. So the theorems are the following. X alpha, x minus alpha. Take the commutator of x alpha and x minus alpha. Yeah? Then this is going to be in Kaplan subalgebra, that is clear, right? Because whatever it appears here, it must have zero root, right? Because alpha minus alpha is zero. So it must be in the Kaplan. That is clear. But the question is which Kaplan element? I mean, can we really say what Kaplan element it is? Okay. Like in the case of SU2, SU3, we had alpha 1 with minus alpha 1. X alpha 1 gave me H1, right? And X alpha 2 with X minus alpha 2 gave H2, right? So can we kind of more say explicitly what it is by using perhaps the Kaplan killing form or something? Can we say that? And the answer is this. Answer is simply it is B of X, some number. This is a number times the point is that it's in this. It is given by H alpha. You see. Some number times H alpha. That is, and more generally, I mean more generally, this is remember our full Lie algebra G. We have decomposed in terms of H plus G alphas, right? Alpha belonging to delta. The G alpha may or may not be one-dimensional. We have not shown yet that it is one-dimensional. It will turn out, but we have not shown that. So more generally, if I take G alpha with G minus alpha, that is going to be some complex number C times H alpha. It's going to be always proportional to this one element, one particular element of the Kaplan subalgebra. That's no, maybe I should stop. I see that the concentration is kind of, yeah, okay. So I'll stop. I will start from this proof on Monday. Because I see the concentration was a bit, okay.